I spent much time with like a bunch of, basically like, Vitalik, Carl, Chengwu, Nicholas Lin, and Georgios. Also kind of, I don't know, Virgil was there. I don't know, there was a bunch of people, but mostly like I spent a bunch of extra time with Virgil and with Georgios in the last 3 days, and we came up with like, a nice kind of outline for a kind of mechanism design questions and like kind of attack path, like kind of methodology for eventually, like, figuring out like exactly what numbers everyone needs to get paid, rather than just kind of speaking in a rather ordinal way about it, like the way we normally do.
Cool.
I feel like I would like to go deep, so maybe I'll let someone else mention what they've done.
What was the attack methodology for?
For mechanism design, like for like the mechanism design problem.
So this is a more general result.
Yeah, it's a kind of a more general, kind of, methodology.
Got it.
Cool. Yeah, so I basically could talk about it. The kind of like the high level shape is basically that we kind of first like identify what the protocol guarantees are, kind of like what we want to incentivize, right? And then we define basically like the quality of like an outcome, which is kind of understood to be like the amount of guarantees that we get for a particular protocol execution or protocol state. Or either we define it of an outcome, which is basically like a kind of the result of the strategies that are taken, or we can define it as actually the strategy profile. So basically we can assign every strategy profile a kind of quality. And the idea there is that, the strategy profile will be like some set of strategies that the participants are following that produces some, outcome, or more specifically produces the kind of desired guarantees that we like outlined in kind of like the first step. And then the second step again is like kind of like define like this kind of quality, which is basically like a kind of really a number, right? For every either strategy profile or every outcome. This kind of like gives us like, a number for every like a kind of like a value for every game, which like should correspond like very precisely to like how much we want to get our desired guarantees. Basically like we might have multiple guarantees, and there might be, so that we might be like having, more than just like a number as a guarantee, but we need to kind of translate that into a number, like basically called the quality. This number is like a function of the outcome or the strategy profiles. And then basically we have, we kind of need to solve a few problems. The first problem is to make maximizing the quality equilibrium under the notion of equilibrium that you are targeting with your mechanism design. And then you basically have to, basically, and then what we're going to do is like kind of after finding making an equilibrium, we're going to kind of maximize the robustness of that equilibrium in that equilibrium model. And the robustness of an equilibrium is essentially the size of the largest perturbations to the payouts that cause the equilibrium to change. And if and we can define this in terms of the quality to say like, okay, here's how much it costs to reduce the quality from this to that, or like more specifically, rather than this is how much it costs. A perturbation in the incentives of up to this amount could reduce the quality from there to there. So like robustness is kind of like a term that is like, not really put in attack terms. So it's not really like it's not really strictly speaking like a security thing, but like, it's like super related to the security question, right? Of like, what does it take to attack it? Because like, if you're like not very robust, then there's like a small perturbation to the incentives that could change the outcome.
Can any of you hear me?
Oh no, V, hey.
We can hear you now.
I cannot hear you.
Oh,
Oh.
we hear you.
Yeah, I'll try to chat with them in the Zoom chat. You can keep going, Vlad.
Okay. And then so basically, and kind of what we discussed a lot was basically this trade-off between so imagine that we kind of have a two-part game. One of them is you decide whether to participate in the game, whether to like put your money into the mechanism, and then two, you like play by the rules in the mechanism, right? So like this is kind of the process of like deciding whether or not to place a security deposit in like Casper, and then the process of like actually playing the game. So we're gonna like think about these types of games, right? Where you need to just basically there's basically an open market of people trying to like decide whether or not to place their money and participate in this game. And then the second part is basically like the actual participation, right? And basically there's this trade-off in like mechanism design, which we've identified and we think is fundamental, that there's a trade-off between the robustness of the equilibrium of the game and the robustness of the amount of people who join the game. When the mechanism doesn't have access to the strategies profile directly, but instead only has access to this outcome, which kind of means that it can only do partial or incomplete attribution of strategies. And so basically, like that's kind of high level overview. You kind of just define what you want out of the protocol, define strategy profiles, figure out how to make that an equilibrium, and or like basically like define the class of structures that have that as an equilibrium, and then like kind of find the one in there that has the most robustness. And then the kind of interesting thing in these games, in the games with two parts, where first you decide whether to enter the game and then you play the game, is that the kind of overall robustness has to be found by finding a trade-off. So the maximum overall robustness has to be found by finding a trade-off between the robustness of the equilibrium in the mechanism and the equilibrium of deciding whether or not to enter and leave the mechanism. And like, I think that's like a super cool result. And like I'm pretty sure that it is like kind of a fundamental result in mechanism design.
Cool.
Yeah. So let me know if anyone has like any questions.
I don't really know much about mechanism design.
Mm-hmm.
I mean,
I've kind of described the process to you. And let me just try it one last time. First, you say what you want out of your protocol. Then you define a score for what you got out of your protocol. Then you have an equilibrium notion, which tells you, given a particular payout structure, what people will do. And then basically you choose one of those payout structures so that under the equilibrium notion, the players maximize your quality, which is like how much you like the outcome of the protocol. And that's like the basic problem. And then the next problem is to maximize the robustness of it.
So this is based on von Neumann Nash style games.
No. It's parametric in an equilibrium notion. It doesn't need to be a Nash equilibrium.
Okay. But the framework of games here is similar to the von Neumann Nash style game. It's not the notion of the equilibrium may be a parameter, but how you axiomatize what a game is, it sounds very von Neumann Nash style.
Okay, yeah. So basically, there's this idea that we have, players with strategies, and that games somehow map those to payouts for those players. but actually an equilibrium notion, usually is driven by that kind of thing in the context of von Neumann. But in terms of just like the math involved in this process, like, you could just imagine that, you have some agents and some behavioral model that is like somehow a function of some parameter. And then you're like tweaking that parameter to make their behavior turn out to maximize protocol guarantees. So, and like,
Okay.
for us, the parameter is the payouts.
Yeah, I'm just trying to make sure I've calibrated, because this is not, Conway style games, and it's not Abramsky Island on games.
Yeah, it's very much like, we make money as like individual agents with budgets kind of game.
Yeah. Okay.
But actually, the kind of math again is more really like in terms of the equilibrium notion. We could probably describe like a similar process. Like we probably describe it abstractly without referring to the game stuff. But like I think the game stuff is kind of relevant because like ultimately we're trying to do is decide the payouts, right?
Right.
And so we end up using equilibrium notions like the Nash equilibrium. But I particularly am interested in coalitional deviations as opposed to individual deviations.
Understood.
So again, let me just like kind of state the process kind of one last time, maybe. Identify what you want out of the protocol. Assign a score to what you can get out of the protocol, and then like set the payout structure so that the players under an equilibrium notion maximize that score. And that's kind of the basic form of the problem. And then the next one is like you want to maximize the kind of robustness of that by like adding a perturbation to the payouts.
Yeah. Okay. Yeah.
So and then basically the kind of interesting result, which we don't have a name for yet, is that like there is a trade-off between the robustness of the of the kind of game where you decide whether to enter the payout system, like, right, and the actual equilibrium of the payout system itself in this partial information context, where the mechanism doesn't get to have all the information; it only gets to have like imperfect attribution of strategies.
I see.
It's really interesting. We'll have to talk about it more sometime when I'm not losing my voice.
Okay. Get well. Drink hot water.
Cool.
And basically the reason why this is kind of the case is that like what can happen is that you can due to like a perturbation in the payout structure, it can happen that like you end up losing money because someone else's behavior changed, and that makes you less willing to participate if you know this is going to happen, or even if you know that it can happen.
I see.
So it basically has to do with the kind of like the shape of the space, like when you like perturb the incentives, the behaviors change, which changes the outcome that the mechanism sees, which changes the way it pays out. And then the question is like whether the way you get paid out can be affected by, say, a perturbation in someone else's incentives. And the answer basically is like, if you want to like kind of maximize the robustness of the incentives in game, you're going to have to kind of sacrifice on the kind of like certainty that won't happen.
That's an interesting result, actually. I'd like to see how you set up the math.
Yeah, right now we just have English, but the math exists in some platonic form somewhere.
Awesome. That's awesome. Cool. Well, Well, Mike and I have a time set up to go over in the next round of the stuff on the consensus as trace. And I was briefly introducing Mike to this next line of reasoning, which is that you now want to consider the a trace where you've only got partial confidence in the agreement. And so what I'm working with to interpret that idea. So this is where where you can have a range of failures, like network drop or malicious behavior or things like that. And so you have only some confidence level in the agreement that you've reached as a result of the trace. And so the thought is to utilize a construction based on the Geary monad, which can be where essentially you've got a probability as monad construction, and you can apply that to the trace monoidal category. There's a nice summary right here. It's like a 2-paragraph summary I can quickly show people. So again, probability has never been something that I've studied very deeply. So I'm always open to help here. But essentially, you're building a category where the objects are measurable spaces. So this is some sigma algebra here, and this is just some set. And then the arrows in the category are these maps, where an arrow from one measurable space to another is given as it takes a pair where you have some element from X and some subset of elements from Y in the measure space, the sigma algebra. And given that pair, it gives you a number between 0 and 1. And there are some constraints on the kinds of maps that you admit. So if you fix a subset in Fy, and so now you have a one-argument function. So then this one-argument function has to be a bounded measurable function. Likewise, if you fix an X and then you let it vary in the subsets of the sigma algebra over in Y, then this is a sub-probability measure for. So it satisfies that it's a sigma additive set function with with f of x of the empty set equals 0 and f of x of y less than 1. And then essentially you build the identity morphisms out of the Dirac distributions. So that's what this is saying. And then finally, composition is given given here. So the measure of the composition. So if you have an f from x to y and a g from y to z, then the composition gf, which is going to take you from x all the way over to z, is given by this integration here. Where and again, I am not an expert in Lebesgue integration, so I have some study in front of me. But essentially, using this for the measure for the integration, right?
Yeah.
Yeah. So this is how you define the composition. And then there are a bunch of proofs, right? So the proofs have to do with, well, you need products in order to do work.
Yeah.
In particular, you need co-products in order to define.
This term reminds me of like this kind of like the composition term. Reminds me of taking the expectation of one of a of the probability of an event drawn from one distribution according to the other.
Yeah, it's roughly like that, right? Yeah, that's they're reminiscent. Yeah, so the tricky part, the thing that requires some subtlety, is that this is defined for relations, and in the real category, what we're interested in, we want this to be defined for relations extended in time. So it's not just relations, but it's relations where, after you've determined that X is related to Y, then you have a continuation, and in that continuation, it may no longer be the case that X is related to Y. So for, as an example, in a resource sensitive system, the act of observing that X is related to Y may use up either, your quantity of X or your quantity of Y. So think about chemistry, for example. So if you have some reagents X or Y, and you have to make an experiment to determine if they are related, for example, if they react with each other, then at the end of the reaction, you may have consumed your quantity of X or Y or both. So at the end of the experiment, the X is related to Y. The continuation of the relation may no longer contain the information that X is related to Y. And that's a way to think about process algebras, as that there are relations extended in time. So then the subtlety is to try to take that view of relations and make it probabilistic. So that's the next step in this setup. And again, the point is to take the trace monoidal construction that I've got, and move it into a setting where we have failure, where you have some notion.
So kind of an immediate thought that I have is that Byzantine fault tolerance isn't actually probabilistic.
No, I understood, but this is about where you've got some, and then what you'll do is you'll relate the confidence to the notion of faults that you're willing to have.
So imagine if all the faults are like deterministic, like say, like I don't know. So let me put it this way. Saying that we have a probability model on the kind of like space of the things that could happen is saying a lot.
Oh, I know. It's asking quite a bit about the behavior either of the network or of the other agents.
Yeah, exactly.
Yeah, it's a heavy-handed approach. Absolutely.
Mm-hmm. And the issue there is that if your assumption is false, then you might run into some issues.
Yep, agreed.
And then normally the Byzantine fault tolerant kind of approach is more of a brute force kind of approach.
Yeah, this includes things like flaky networks and.
Mm-hmm. So the question, but does it solve that? Does it answer the question of say does there exist a possible protocol execution with this property such that two nodes disagree?
Yes, you can certainly answer that within this framework.
Right. Not just within some probability. Yeah, I mean maybe if everything has some probability, and then if you can ask you
can ask, is there a non-zero probability for?
Yeah. Okay. So you might just be doing you always be adding, like having more information and like not missing on anything.
Yeah, I think that's correct.
Okay.
Yeah.
So as long as you're not like missing like the ability to ask like the kind of non-probabilistic fault tolerance question.
Yeah, agreed. I mean, and in general, you can always collapse this down to, you know, situations where every event happens with certainty, right? This embeds into that. So the category rel embeds into the category srel.
I see. Oh, yeah. I mean, I guess I believe that. Yeah.
But again, cool. So anyway, that's my update.
Cool. Carl,
Anyone else?
Yeah,
Mike?
yeah, sure.
Carl.
So, if only Vitalik was here. One update that's not mine, but that I just feel like should be noted is Vitalik's working on his description of the Casper the Friendly Finality gadget, and that's going to be a pretty comprehensive overview of all the different designs and decisions made.
Yeah, and in that doc, he does like talk about and like reason about this trade-off between the like your decision to enter the game versus like the robustness of the equilibrium in the game, and he like looks at the griefing factor kind of analysis that corresponds to that in like kind of a very large amount of detail. It's definitely cool, and I love the kind of name convention of like resolving the kind of Casper name collision by saying Casper the Friendly with X.
Yeah, exactly.
Yeah.
So
like most of the time I work on Casper for the Friendly binary consensus protocol.
Yeah, I love that. And there's so yeah, last week one of the just as Vlad said, one of the main things that we worked on was the class of attacks, like the discouragement attacks, where you essentially through some kind of griefing discourage new validators from joining, which then affects the kind of repeated game of do I become a validator? Yes, no. Like if yes, then the other game of actually being a validator. So that was like a major focus, and I think we came up with some ordinal results and have some reasonable way that we're reasoning about this. But I think that like Vlad, what you were working on is super, super interesting, and I think we should like take it definitely leaves a lot of room to take it further.
Yeah,
and
and to be fair, Vitalik's also looking at like cardinal numbers, or like or just like scalars.
Yep. Sorry, continue.
No, you.
Okay, so I and other than that, let me see. The main update is just like on the development front. Basically, there's a slight change to fork choice or possible modification, which we may or may not use. That is basically done, and there's also a bunch of a couple developers, Chengwu and Nicholas being two of them that were there last week, that are also helping out with both the daemon and the actual Pi Ethereum implementation. So that's exciting.
So what's the change in the fork choice rule?
The change in the fork choice rule is there. So before it was basically you choose the checkpoint that has the most commits, and the most commits being a percentage of deposited stake that has been committed versus total. And then once you've chosen that, this is where the kind of new fork choice flag is enabled, where you then choose the fork which has the most prepares, just like the heaviest in terms of prepares. And that is, there's some things that I think need to be reasoned about to pick one over another. Definitely curious if there's any feedback.
Sorry, I didn't actually hear two of them. I thought I only heard one. So go. I thought like so. The question is like, do we just go with the commits, and then the longest chain, or do we do commits and then proposals?
Exactly. So it's commits and then longest proof of work chain, or longest chain period, and then commits plus prepares, and then from the prepares checkpoint, you then do the longest chain.
Right.
If that makes sense.
Yeah, that makes sense. So I mean, the question is like, is there a penalty for getting the prepare wrong?
Yeah. And
if there is, then I think that that fork choice rule is pretty reasonable.
Yeah, there's definitely a penalty. The scary thing is maybe, or at least one scary thing is like validators just being weird and kind of preparing they're like two competing forks, and one gets some prepares, another one gets, and it's just like,
and it could oscillate back and forth, and the idea and the question is like, like, are they like strongly incentivized not to do that, right? And is that like a thing
exactly
right? So so it is kind of sketchy, but like and the thing about the commits is that like that there's already 2/3 prepares, which kind of enforces that like there won't be competing commits at that height without slashing.
Yeah, for the I mean, I guess you can still have some of that, but I think it's significantly harder to get into a state where you're going back.
Seems like a risky fork choice, Will, Carl.
Yeah.
For now, anyways. I don't know.
Yeah, we're gonna just have it as a flag, so we can kind of figure out if that's really necessary or not.
Okay.
I mean, we should
really
honestly reason about it.
Really safe or not? As safe as the first question.
Yeah, exactly. Yep. So I think that's about it. It was definitely a hugely productive week and a lot of fun.
Yeah. Yes. So I would like to kind of like go over a little algorithm for calculating precisely like the numbers of like the payouts. It kind of more detail than I kind of spec'd out earlier. It was kind of just a high level picture. So basically, one of the kind of questions that I kind of mentioned earlier, which didn't really like kind of resolve, is like whether you should assign qualities to strategy profiles or to outcome. But if you assign them to strategy profiles, then there is a pretty easy way to calculate what the mechanism payouts should be if you're like willing to like allow yourself like one assumption as like a parameter, right? And basically the idea is like for you basically assign them kind of like a hypothetical payout for every strategy profile. So the kind of the payout they would have gotten if that was really their strategy, if like the mechanism really knew, like if the mechanism had full information. So basically that's kind of the version of the story. Like you if you assign the qualities to the strategy profiles, then you can ask, how would I solve this mechanism design problem in full information? So then you kind of do that, right? Where the mechanism has access to everyone's strategies, and then you kind of come out with this like hypothetical payout for every strategy profile. And then what you do is you kind of have like, okay, instead of observing the strategy profiles, we only observe some outcome of the execution of the protocol. And from that, we have kind of like, can compute this strategy inference thing, which is like this pre-image problem. And so, we have the fact that like the strategy profile that actually happened is inside the set of, which is basically the inference function of the outcome of the strategy profile that actually was played. So strategy profile that actually was played to produce an outcome, and like the mechanism is able to do inference on that to see what strategies might have been played. And then basically, like, the assumption is like, okay, now you have to pick a distribution over that set, over the set of possibilities that like might have been played, like all the other, kind of the strategy inference set, like all the strategies that might have produced this outcome. And then you basically just take the expected payouts according to that distribution from the payouts given in the full information version of the game. And then the kind of the next kind of question is like, is it reasonable to assign quality to strategy profiles as opposed to outcomes of the game? And the kind of intuitive answer that I have is that, like, if you have a protocol that actually is can be provably solves, provably. So basically, imagine that you have like a strategy choice in mind, which maximizes your quality. And I think like in that context, it makes sense to say, okay, I can kind of say how much I like every strategy profile. But if you don't know which strategy profiles actually increase the quality of your output, of your outcome, then you kind of have an issue, right? But if you kind of have kind of solved the problem of producing good outcomes using choice of strategies, then you should be able to assign qualities to the different strategy profiles, and then the qualities of strategy profiles basically will be something that you can, through this process of like imperfect inference and assigning distribution to the set of possible strategies that might have been followed, we can kind of average out the payouts that we would have in a complete information game to get the payouts that the mechanism will assign in the partial information game. It's quite nice in a number of ways, because it's very like the algorithm is simple and intuitive. However, the only way in which it's parametric in your equilibrium notion is in the sense that the game you solved in full information was parametric. Your solution was parametric in your equilibrium notion, and the kind of issue there is that maybe actually the equilibrium isn't going to be the same in this expectation of under this kind of like average of things that might have happened. Like there's basically there needs to be like some kind of proof that the somehow if you maximize robustness in the full information game, then this will translate to maximum robustness in the in using this kind of like average thing. And then the other way to say is, okay, maybe our job is to pick this distribution in order to maximize robustness, which we kind of like measure externally.
So what data structure characterizes a strategy profile?
It's a map from like the like kind of in Casper say it's a map from like validators to it's basically from validator names to like validator like programs that like they're running. So basically the question is like, what software do they choose to run?
So what characterizes a strategy profile? Is it
basically
like a computable function?
Well, I mean, you remember our like fault model?
Mm-hmm.
Like exactly that. So basically, you just think about all faulty executions of a program, and like that's the behavior space. At least in our context, where we can tell the validity of protocol messages, and so like that kind of dramatically reduces the space there. So basically, it's all faulty executions of the protocol program is the strategy space. Plus also correct execution. And also notably plus the network, because like if you don't have the network in there, you have kind of another degree of indirection that needs to be added in somewhere else, and might as well kind of put it in here.
So It sounds like what you're saying is any behavior, because it's all faulty and all correct behaviors.
Yeah, but basically that's not quite any behavior because like it's only behaviors that produce protocol messages.
Yeah, but for example, I could go off and calculate a random digit. You know, I take a random distance and calculate that number, that digit of pi, and then produce a message, and then go off and calculate 10 of those, and then produce a message.
Yeah,
and then
as
go
long
off
as from like the outside, like we could model you as like just like someone who isn't doing that pi stuff, then like it's fine.
Okay. So basically, any computational behavior. So any computable program here is accepted.
No. So like what I'm saying is like only the faulty. So you like again. So let's just do this. Let's just do
Because a faulty
wait, Greg. Let me just do the kind of the like translation from like a pi calculus process to what I see as like the all faulty executions of that process, which is you'll see is like a subset of what you're talking about, right? Like a very small subset. Basically, I'm only going to like allow a small number of things. I'm going to allow, it's basically whenever a process receives a message, it has a non-deterministic choice to drop it before it actually gets to the validator. Whenever it sends a message, it has a non-deterministic choice of dropping it. And between every two processes, if they're communicating to each other, they have to actually communicate through the network. The network has basically. It receives things, it adds them to some kind of collection, and then it like non-deterministically spits them out on the other side.
Yeah, but I understand.
And then,
but that doesn't.
and then finally, wait, one more. There's one more fault where basically you take the validator process, and then you make an arbitrary number of copies of it. So basically, we have like these on every channel we have this network as an intermediary. And every channel and every connection between us and the network, we have another intermediary which non-deterministically drops things both ways, and then every process is replicated, and then like that corresponds to what I'm seeing is all possible executions in this context where we kind of know that the protocol process is running, but it might just be running in a faulty way. Namely, it might be kind of dropping messages. It might be making multiple copies of itself instead of just running one like it's meant to, Oh, and the network might be doing random stuff. So like we're really not looking at all programs. We're only looking at this pretty like restricted set of replicated protocol programs which like selectively accept and send messages, and a network that like can like do that in all possible orders.
Well, if I understood you correctly, then a program which takes no input and goes off and calculates pi and produces no output is legal in that setting.
So basically, I'm like that. I don't know how you can say that it produces no output if it's it's pi calculus process. Like it's obviously passing some messages wrong. But I'm just no. So like I don't know, Greg. Like I'm not really ready to talk about that edge case. Like I mean most of the operations had to do with communications. In fact, like everyone had to do with like communications in some way. So like I don't know, you can obviously replicate it and then not communicate and not engage in any of this thing, and it's like kind of fine. But like
I'm just trying to get a handle on what constitutes, like how we would recognize when we've got a strategy versus when we don't. And so since you can drop inputs, you could drop them all.
And you can drop outputs and you can drop them all.
You can drop them all. And so now we can have programs that calculate anything in between.
But basically, no. The only programs that are allowed is the replication of the protocol program.
What's a protocol program? That's
A
what I'm trying.
validator, a validator code, just like validator code. Like, you know, whatever.
I understand, but
consider now validator
is there any constraint on validator code at this point?
Yeah, it's like absolutely just like, you know, one program. Like that's just like the one protocol program, like the one select thing.
Okay, so you can't have validators in the wild. Like it can't be that a third party vendor writes a validator program and decides to run that. Everybody has to go to a single central source and say, okay, I'm running this, and I have.
You know, that's like kind of like not that's like a later stage like thing. Like at first yeah, like actually having that property is like a property of a protocol, not of its faulty executions.
I didn't quite follow that. Anyway, so it sounds like there's still some work to be done on tightening up what constitutes a strategy profile.
No, I think I've been like super precise. Basically, like, so so imagine, okay, so let's do Bitcoin, right? Let's just, because like where we know what the protocol process is. It's like you download the blockchains that you see, you mine on the heaviest one, and like that's all you do, right? And basically, like, you know, the question is, what are the behaviors that are possible if you make copies of this program and like selectively give it inputs? And like those are all the strategies. So you basically run a Bitcoin node. You have to run a Bitcoin node, or you could run n of them, and then you like just decide what you selectively give them and what you selectively pull out of them. And like that's the only, like, you know, the only thing that's a strategy.
Okay, but running a Bitcoin node, I guess the important thing there is how do I have confidence that a party is running a Bitcoin node? This is, I've got a checksum.
You don't need to in order to reason about the fault tolerance of the protocol, because only protocol messages can affect the state of the protocol, and basically you can model any protocol message to have been produced by one of these things. And so we don't need to consider the set of all crazy strategies. We can consider only the ones that like kind of, you know,
Well, I mean, couldn't an attacker
just give us enough coverage of like the whole attack surface?
Couldn't an attacker, you know, produce valid messages, but not really run the
and no matter what, sure, but no matter what he's doing, I can produce exactly the same messages in exactly the same way using this process that I just described, using a strategy in this field, in this set.
Okay, that would require a theorem.
Yeah, well, I mean, you know,
that's not immediately clear.
I know, but I mean, this is like the result in the fault model that we kind of.
So I think he's doing something kind of like barbed by similarity, in that the protocol messages are the barbs. So the only things you can see about the
yeah, I know, but you can still do all kinds of things with barb by similarity, right? That's exactly what I had in mind when I was probing his definition.
I don't think there's anything wrong with going off and computing pi in between. It just makes for a slower execution.
Right, but what that means is that the total number of strategy profiles is exactly equivalent to the set of all computable functions.
Yeah, but we don't need to consider all of that because, like, you know, there's like only like some equivalence class that is relevant for the fault tolerance of the system.
So are there deadlines that occurred during the protocol? I mean, because
there may be, but you know, it's easier to think about like protocols where you don't have any synchrony assumptions in this context. Right?
I just meant that what you end up needing to consider is permutations of the messages that are being sent rather than all of the behaviors in between them.
Yeah, that's I think that's exactly right, and I think that's you know, and I think that like my set of programs basically like defined by like faulty executions can like produce all of these orders.
Well, the reason I was saying you need to consider more than just the permutations is because if you have an algorithm that takes as input strategy profiles, then you have to be concerned about what's the number, what's the kind of thing that you want to recognize as your input. That's why I was worried about the mechanism design algorithm. You want to,
of course, but basically, like, we can look at it, like through the lens of a fault model, as opposed to through the lens of like all possible processes.
Yeah, I understand, but so far the fault model is not restricting the shape of the input.
It is restricting. I mean, it is absolutely. I mean, there's super strong restrictions actually. Like the only protocol messages only messages that are produced by the protocol program can like fly across the network. And so that means that like you can model whatever's on the other side as something that like runs the protocol program somehow, and gives you something. Kind of like the idea is that like so imagine if here's the protocol, right? You take the messages.
So Vlad, I understand your argument. I just don't believe it, right? And the reason,
I think it's like it's super clear for a set of protocols where you can verify whether the output was produced by a protocol process.
Okay, so that's what I'm trying to get. So are you saying that the input, the shape of a strategy is guaranteed by a checksum, or are you saying that the shape of a strategy is guaranteed by something more relaxed? If it's if you're saying
I see the issue. I see the issue. Sorry. I should have mentioned. Basically, imagine like whenever you receive a message, you do this like type check on the message, and then like if it doesn't pass, you drop it. And so like only messages that like pass this type check like can get through. And basically, this is what we think of this as validity. Like, is the block valid?
No, but that's not sufficient to guarantee. That's not sufficient to guarantee the space of all programs. Because programs
it's sufficient to give us like an equivalence class of programs that can build blocks in all faulty ways.
But it isn't. That's what I'm trying to argue.
So like let's take a really simple example, Greg. Right? And it's basically almost exactly the Casper protocol, like as for the binary consensus. Only we're going to drop the estimates. So you have a justification and a sender. And then a justification is a set of these messages, which each have justifications and senders, and the justification could be an empty list or like, basically a list of these things. Then basically like the protocol program is to take messages you receive, list them, append the sender, which is just kind of your name, and kind of like wrap that in brackets. So like the protocol program is, receive messages, put them in a list, append my name to it, and then that's it. Right?
Okay.
So this is what the protocol kind of expects, and if it ever receives any message that doesn't have that shape, it is kind of out, right? And then the question is, okay, how can we think about like all ways that this like protocol could possibly evolve? And the answer is basically like, you have this protocol. So that like basically all it does is it appends a name to a list of messages I received and sends those as messages. And like we're asking about all ways that this protocol could execute if these nodes are faulty. And the answer is like, okay, maybe they crash, maybe they miss messages, maybe they don't send messages, but like and that's about it, right? There's no other real anything that they can do that to like affect these data structures other than not receive messages, not send messages. In this case, like you don't have to worry about the replication because it's not stateful. And that kind of like somehow gets full coverage of all of the possible outcomes. So we don't really need to like.
I understand. I understand that in this restricted case where you have a clear specification of the algorithm. And the algorithm is in a restricted expressiveness category. Like in this particular case, the restriction is regular. But as soon as you get to context free, you're out of luck.
Okay, yeah.
There's
So,
a lot more
I
things.
think
There's a lot more that you can do, and
So
and
maybe-
regular expressions is not sufficient to run a, like even the Bitcoin protocol, let alone what we're
Right.
trying to do with Casper. So
I mean, I don't know enough to say kind of what my requirement is. But basically, as soon as you have state, the only thing you really need to add is this replication thing, where basically you basically take inputs and then you and then you send them to every copy of the program that you have, which then each can decide whether to drop them. And so you're running an arbitrary number of the protocol process in parallel on optional inputs.
maybe what you're saying is that you're enumerating the list of variations of some algorithm that you're allowing, and
Yeah,
so
it's all faulty executions.
well, no, under the definitions you've given, that's not correct. But what I think what you are doing is positively enumerating the different changes you can ring on a particular algorithm.
Sure. So it's a model. It's a model of all of observable faulty executions.
Well, I mean, I can certainly agree that if what you're saying is that the total number of protocol variations that you're allowing is generated by this closed set of operations, then yes, that is a much tighter set of programs. But if you're trying to do it from the other direction, I don't believe that that's sufficient. It may be necessary, but it's not sufficient.
Well, so I basically
and I can come up with
so I think I kind of go both ways. I kind of think basically I think about the equivalence class of programs that produce the same outputs and inputs. Sorry, on inputs. So if there's no observable difference between program A and program B in from the messages they produce, I put them in an equivalence class, and then I pick a representative from every equivalence class.
The problem is that the network can do reordering, and so there are all kinds of algorithms that
yeah, of course. I mean, the network is a totally separate agent that is non-deterministically ordering all the messages in this model.
Right. So right, and so because of that, then you have to be able to you have to positively say, I'm only allowing these variations from some source program, some initial program, or if you take it from the other direction, because the network is reordering things, you can have all kinds of algorithms that are not included in that set of changes that you're ringing on the initial source program.
I think the kind of I mean, unless there's clocks going on, I think that just by non-deterministically holding back inputs. Oh no, reordering. Reordering. No, I can get reordering through network faults. Yeah. So basically,
but that's my point. That's my point. Because
and that's what I do. I kind of take this global view where I see the network and the players in my fault model.
Yeah, I understand, but that means that you have to admit algorithms that can't be generated positively by the set of changes that you're
no, because it's I still get coverage of all of the. You're right. So I mean, basically, rather than thinking about the messages that come out of validator, I need to think about the messages that come in to a validator from another one. So basically, right. I don't judge you based on the messages that come out of you. I judge you based on what messages that come out of you through the network to me.
Yeah.
Yeah. Sorry. That's good. That's a good point. Cool.
No, it's so. But now I have a much clearer picture of what you're saying, and that actually makes a certain amount of sense. What you're saying is, and because it's calculatable. What you're saying is, there's some original source program which is a source of truth, and this could work, culturally. Like everybody can go to some repository or some collection of repositories that they trust, and they're going to get some variation, some version of the protocol. And then you're willing to admit either that original source program or any program that can be gotten to from a series of changes from that source program. And here's the kinds of changes we admit. That I can grok, and that's checkable.
Right. Yeah. I think that's actually a fantastic way to put it. So basically, let me see if I can put it in my kind of English. A node only considers the ways that people that other nodes could change its state, and so they only needs to look at a kind of subset of things, and you kind of can model them as a subset of programs.
Yeah, right. But that subset of programs is generable from some initial starting program and a set of changes that you're allowed to admit on those programs.
That's kind of what I'm saying. Yeah.
That works. That works. Well,
Yeah.
So that's interesting. I appreciate your patience.
No worries. I mean, this turned out to be much more interesting than I anticipated. I thought it was, just trivial stuff, right? I would love to see, the math on that in kind of more detail.
Yeah, I mean, that one I can write down. That one I understand clearly enough. I can write it down relatively simply.
Cool. Yeah, because I would love, I would love to see it written down more formally. Because right now, I kind of basically I'm kind of being a little bit abusive with some of my notation, just because I kind of see it at a higher level of abstraction. I don't need to think about. Yeah, I just kind of step in and remove a whole host of possible messages and a whole possible programs without much second thoughts.
Yeah, I get that. Well, in fact, what you're doing is what you're doing there is reminiscent of what I'm doing with the trace. But what I'm saying with the trace is here's an equational characterization of the programs I admit. So what you're saying is you begin from some program, and then you can run these genetic changes. They're not quite genetic, but roughly speaking, from that source program, here's a set of rules that you can use to operate on that program to get new programs. And when you take the closure of those rules over the source, then that's the set of node programs that could be running. And what I'm saying is, I don't care.
Sorry, go on.
I'm saying I don't care what your source code is. You have to prove to me that your source code satisfies these equations. And that's the trace model. So the trace model is very insistent. You have to satisfy yanking. You have to satisfy vanishing. You have, it's this list of 9 equations. If your source code provably satisfies those equations, I'm good. I don't care what you're running.
Sure. Yeah. I mean, so to me, this isn't exactly, I'm thinking kind of about an equivalence class, on faulty protocol executions that can be, modeled, based just on messages I receive on my node.
Yeah.
And if two things are modeled the same way on that, then I consider them to be kind of in the same equivalence class, and I pick basically the representatives that I think are the most kind of tractable. But basically, how we actually reason about the strategy space is going to end up being, maybe super important to how we actually in practice can end up calculating these scores, right? We're gonna need to solve this mechanism design problem as a function of the strategy space, right? When in Vitalik's finality gadget, it's quite a simple story because he doesn't really deal with he basically like has this like round based thing where there's a relatively, it's actually like I think it's like the smallest traditional consensus protocol I've ever seen, because basically what it does is it finalizes outputs produced by a blockchain. And so basically like it kind of gets to piggyback a little bit, and then like it kind of like there's requires like 2 rounds of communication, and there's like 4 slashing rules, and kind of it has like all of the kind of relevant proofs.
I mean, it's way simpler than Tendermint.
Yeah, it's simpler than Tendermint, which is, and Tendermint is simpler than PBFT.
That's right. Yeah. Yeah. So, I mean, I think this is a really interesting point. I think we're kind of coming at it from the same viewpoint. Like, what is a characterization of strategy that we're willing to admit in order to run certain kinds of algorithms? So the algorithm I was interested in running was essentially to formalize Vitalik's insight that I can start with the traditional consensus protocol, and I can produce one that uses slashing conditions.
Mm-hmm.
Which means I need to know when you've handed me a consensus protocol, because if you've handed me gibberish, or you've handed me, I don't know, bubble sort or whatever,
mm-hmm.
Then the algorithm may not work, right? I need to be able to kind of type check that you handed me a reasonable program.
I don't think anyone, Greg, I don't think anyone in the world has ever figured out how to type check consensus protocols.
Well,
I don't think anyone is even close as far as like it's the traditional literature goes.
Right. So I think we're kind of nailing it. I'm feeling really confident here. I think we're nailing it. I actually believe
I can't.
Notion of trace nails what consensus is. Trace.
Interesting. So,
yeah. That's kind of what I'm. And I could be wrong. I'm wide open to possibly. I've massively screwed up somewhere. But
no, I mean it sounds super cool. So if you're right, basically what you're going to be able to do is do interoperability with much lower overhead.
That's the idea. Yeah, that's one of the benefits. But frankly, to me, the biggest payoff is to formalize Vitalik's insight, because then you open up this world, right? So like a huge number of consensus protocols that were traditional suddenly can be recast in this economic incentive light, right?
Cool.
And which was kind of the door that Bitcoin opened in the first place. Right. Bitcoin said, well, what if availability is more important than, correctness? What if you maximize?
Yeah. And it also did the whole like incentives thing. There's a bunch of, it's really, so here's kind of so Bitcoin, I wonder if it satisfies your trace, because it is a peculiar algorithm compared to like, normal consensus protocols.
Yeah. So I think Bitcoin satisfies the trace thing, but the question is there a pre-image? Can we run the algorithm backwards and arrive at the consensus protocol that was the source that gives you proof of work? And I'm not sure that we have such a. That's such a
that seems ambitious, but however, like it would be really cool if you had like say like some kind of like correct by construction simplest consensus protocol.
Yeah, or a proof, for example, that Vitalik's protocol is somehow minimal in some lattice.
Yeah, I mean that's like just as good, right?
Yeah, that's right.
But I mean what I kind of I'm seeing is that like there's when you look at fault tolerance, there starts to be trade-offs, and so there's not going to be like a unique best for all possible fault contexts.
I agree with you there. I agree with you there, and I don't know that there's a there's an on-to relation. Like there may be like slashing condition protocols that don't have a pre-image.
Right. Then meaning that there's no way to implement those conditions.
No, that they didn't ever, they don't arise naturally from some traditional non-incentivized version. It seems like there could be lots and lots of, you know, slashing condition based protocols that just, you know, they can't be expressed as, you know, an incentivized version of a traditional protocol.
Yeah, so that is something that I'm extremely curious about. Actually, I don't know if I, you know. So the question is like, okay, well, if you can't think of a protocol, can you even satisfy it, right? Does this market have any hope of making any progress if there is no way to implement those, so a program that like kind of gets, you know, like doesn't get slashed in those rules, or somehow gets rewarded in those rules.
Yeah, I mean, I think all we're saying is that the only way to implement this protocol is with incentives. You can't discretize it with, you know, into some, you know, just, you know, binary voting, prepare, commit, done.
Yeah, kind of. I mean, so I mean, incentives, but also there's like this kind of idea of like like once a node is like, you know, if you can like fully attribute a fault that isn't like a potentially honest fault, then like, you know, you just kind of ignore all future messages from that, and that can be effective. You know, even though there's not like a direct incentive.
I confess I've got a meeting at 9 and I've got to do stuff between here and there, so I should probably jump off.
Yeah, this sounds good. You know, I'm excited about this call. It was cool.
Yeah, I thought it was very interesting for sure.
Sweet. Yeah, I mean,
I hope you picked up what Mike was saying, which was that the notion of equivalence that you've got amongst your nodes is characterized by simulation.
Yeah, so I didn't really understand that, but you know, I'm gonna try to, you know, catch up on.
Yeah, well, I know you and Mike have some time scheduled, so.
Yeah, I'm excited.
Okay, guys, this was really fun.
Yeah, cheers.
Yeah.
I'll talk to Christian after this to get him to like maybe crop certain parts of the conversation so we can share them a little more widely.
Yeah. So I'm gonna start the